Yeah, oh, okay.
Is it possible to have the present on this one? No.
Oh, sure. In that case, like listing of I need to figure out which zero will move the mouse.
Okay, and that's great.
Oh, hopefully it works. Okay. Anyway, we are very happy to have Rohan Goyal visit us again. Rohan is a frequent visitor to our department, almost as frequently as Prahlad. So Rohan is a PhD student at MIT. He works with Yale Kalai, and he also works with several other people. I mean, like, he's going to be telling us about this recent work with Venkat on optimal proximity gaps in codes.
Thanks for the introduction. So yeah, this talk is about this recent work about optimal proximity gaps. I'll try to define everything because this is a relatively new problem. But please ask me questions, stop me at any point. I'm happy to take questions. But yeah, good. So what is the motivation or what is the problem? So this is a problem that is very much a coding theory problem, but the motivation came not from coding theory, it comes from proof systems. So often in proof systems, you can reduce the problem to checking if some elements are either close to a code or far from in the code or far from a code. So you want to check if U0 and U1 are in some code or delta far from it. So instead of checking each separately, often you just take a random linear combination and hope that if either was far, then a random linear combination is far. So the question that comes up is, when is this okay? When is it okay to take a random linear combination and you'll be happy? In particular, up to what distance parameter and what is the error? What is the soundness of this? So this is the question that comes up, and this is what we'll try to talk about. Good. So let's just give you some background. So codes. So a code is just some subspace of some sigma to the n, such that every pair of elements is far. So when I say far and when I talk about distance, I mean the Hamming distance, and I mean the normalized Hamming distance. So what fraction of coordinates do any pair of coordinates?
Subspace, not a subset.
Yes, so it's coming up soon. So distance of the code is how far the minimum distance across two distinct code words, and the rate is how much information there is in this code. How much information there is. So if you think of the sigma to the k words, the k bits of information, then k by n is the rate. You can also think of what fraction of the bits are information bits. Information. Good. Codes 1 or 2. So this is what you were saying. Sigma to the n. The kinds of codes that we care about are linear codes, where the code is a linear subspace. And the alphabet is some finite field. The other kind of codes that we'll care about are additive codes, where each alphabet symbol is not a single finite field element, it's a few finite field elements. It's a low dimensional vector. Good. And I'll give you examples will come up soon. Good. Is the setup clear? Is the coding theory setup clear? Good. So what is this problem of proximity gaps? So an additive code has a delta comma epsilon proximity gap. If you consider any line in the ambient space and greater than epsilon fraction of the points along that line are delta close, then the entire line is delta close. So you can think of it the other way around. If anything is far, then more than 1 minus epsilon things will be far. So this is exactly the kind of property that we want from the motivation. You can ask for something slightly stronger, which is often very useful as well, is correlated agreement, which says that I'll tell you something stronger than everything along the line is close. I'll tell you that the reason for this closeness is that there is a line in the code space, which is delta close. So you're not just close to the a particular code word, you're close to an entire line. And that is the reason for this closeness. Good.
So I should be thinking of epsilon as very small, right? In the sense that
Yes,
you want to say
negligible.
even if for non-negligible
Yes.
fraction of them, okay.
Good, but it's fair to ask even for not negligible, because you could try to amplify maybe.
Okay.
By taking a few examples. Like even if you could ask something like this for 0.01, that is maybe still interesting for some application you have in mind. I just want to give you more than good. Okay, so the kinds of codes that we'll talk about are these Reed-Solomon and polynomial evaluation codes and related codes. So I'm guessing many people have seen this. The Reed-Solomon code is you take a polynomial of degree k or less than k and just evaluate it on many points. And so that's the Reed-Solomon code. So the set of codewords is just the evaluation sets of polynomials of degree less than k. And these alpha are just the evaluation points, n is the length of the code, k is the degree, and q is the size of the field. So quick sanity check, like the rate here is k by n, because you have k by degree less than k. And the distance comes from the fact that any 2-degree polynomials of less than degree k, their difference is also polynomial of degree less than k. And a polynomial of degree less than k cannot have more than or at least k roots, unless it is received a polynomial. So this means the distance is 1 minus n k over n plus a 1 factor, which are big one. Good. Good. So standard setting of Reed-Solomon codes, you can imagine that these evaluation points are just some arbitrary distinct elements of the field. But there are other, you could try to come up with explicit interesting points for which the code may be nicer. You could try coming up with points in other ways. One of those ways I've talked about is random Reed-Solomon code, where the evaluation points are chosen.
Go back to the definition, I want to check something.
Yeah.
The delta epsilon definition.
Sure.
Interesting. So you're not, for me, I would guess the definition would look like if it's delta close for an epsilon fraction of points, that it's 2 delta close for everything. You don't lose that.
No, I don't want to lose any. But that should follow kind of immediately in some sense. Because if you had 2 points which were delta close, then you could appropriately construct another point which would be 2 delta close, like just by triangle inequality for any point. So the 2 delta definition won't be very
Something like some factor 1.1.
Yeah, okay, so good. So you can ask, maybe if I relax this a bit, maybe I don't want delta exactly. I want something slightly worse than delta. Can you get better error bounds? And that is a very fair question, and I will say something about it at the end. But for now, I'll stick in this very strong regime of exactly this. Yes.
Alpha and
Alpha is from the field. Like,
same field as
yeah. And so since these are additive codes, they were like vectors over a field. So the field over which they were linear.
And I should think of delta. Wait, so what was this discussion about negligible versus 0.01?
So what epsilon you should think of was the question there.
But cannot be, it has to be 1 over q, right? The one of the big size.
Yeah, but q you can take to be very large.
Okay.
Typically in Reed-Solomon, because you need n evaluation points, q is large. But this is like, the statement sort of says that, if for a really small but constant, let's say 0.01 fraction of points, you somehow notice that u0 plus alpha u1 looks like a Reed-Solomon code. You sort of want to say that must actually happen not just for a small fraction, it must happen for everything.
Good. So random Reed-Solomon is when these evaluation points are chosen randomly from the field. And then folded Reed-Solomon is in each coordinate. Now, since in additive code, I can put few evaluations. So instead of putting just one evaluation, I put few evaluations. So Whereas like each coordinate was f of alpha I, now it's like f of alpha 1, f of alpha 1 gamma, f of alpha, so and so on. It's not immediately clear why this is helpful, but we'll talk about it. Good. So, what was known before? So, the best known was for just standard Reed-Solomon codes. Beyond that, so this result of Venkatesan, Kalman, Ishai, Kopati, and Saraf from 2020 showed that standard Reed-Solomon codes have correlated agreement property, or the proximity graph property and the stronger correlated agreement property up to this distance, which is like 1 minus root r, where r is the rate. So 1 minus root r minus epsilon. And this 1 minus root r quantity might seem strange to you if you have not seen it before, but it is the Johnson radius, or up to which we know list decoding for Reed-Solomon codes. I'll talk about it in a bit. So, but up to 1 minus root r minus epsilon. And initially they had like n square points if n square field elements. It was happening. Now it has been improved to n field elements. If n over poly epsilon field elements are there such that these points along the line are closed, then the entire line is closed. So it's quite nice. Like n square was kind of bad, but n seems more satisfactory, and I'll get to why.
Sorry, and if your delta was like 1 minus r by 2, in that case the other parameter is 1 over 2.
No, then also you need n over q, like the poly epsilon will go away if you're thinking of less than.
Poly epsilon goes.
The thing you're thinking of, like at 1 minus r minus epsilon, if you allowed an epsilon slack, sorry, a distance by 2 minus epsilon, if you allowed an epsilon slack, then it will only be 1 over epsilon.
It would, okay, so in
But
that case,
since
it's 1
our-
over r.
Yeah, but since our slack is just like 1 by n, it's like 0 slack, right? 0 slack is like 1 by n
So
slack.
this is about reaching half the minimum distance of the code and being epsilon away from.
Yes, that changes the one. So, like, since your guarantee is exact, as Rohan showed it, that is. So, where does this come from? They basically use the list decoding algorithms for standard Reed-Solomon codes by treating these entire lines as a code word in some sense over some different field. I'm just saying this way, it's a very clever, very a lot of nice
Is there a Q versus N dependence that the statement requires apart from what shows the point? Like Q is at least N definitely, but should Q be
not
yeah,
I don't think so.
Q being bigger than whatever N is N.
That's enough. So you can even just think of it like how many points along. You don't need to worry about the fraction. That's it.
Right.
So it's just like the number of points. And again, it will slightly become clearer why this is coming in soon. Right. And the problem here seems to be that we don't know better list decoding bounds for standard Reed-Solomon codes here. And these recent works suggest that you need to prove better decoding bounds first for standard Reed-Solomon codes if you want to get proximity gaps that correlated agreement. Okay, so I've been saying this word list decoding for a while. Let me just define it quickly. Code is delta comma L list decodable. I have the formal definition, but all it's saying is if around a point, or if you draw a delta radius ball, it must have at most L elements. So usually you might think a radius distance by 2 ball has exactly at most one thing. Now we are interested, can you go beyond distance over 2? And at radius delta, if there are at most L things, the code is delta comma L list decodable. And give a slightly weird perspective on this, which is among any L plus 1 code words that are delta close to any element, 2 must be equal. And it will maybe become clear why I want to take this perspective. So list decoding capacity says that, okay, I'm lying somewhere here a little bit, but okay. Basically, at distance 1 minus r plus epsilon, list sizes are going to be exponential. So you can't do list decoding ever. And for some codes, there are codes for which at distance 1 minus r minus epsilon, list decoding is possible. So we don't know this for standard read solvent. The question is, for what codes do we know this? So if you want to go down to one. No? So what are the codes? In 2006, Guruswami and Rudra showed that there are these folded read solvent codes that I showed you earlier do achieve list decoding capacity. So they do go up to 1 minus r minus epsilon. Recently, Chen and Zhang showed that not only do they go up to capacity, they actually achieve the optimal list sizes as well. So you can't get better than 1 over epsilon list sizes, and they show that these codes in fact do get 1 over epsilon list sizes. And in other work, Ravia, Guruswami, and Lee, and Goyal and Zhang showed that random read Solomon and random linear codes also have this property, that they are list decodable up to capacity with optimal list size forms. So the question is, can we actually use these codes instead of standard Solomon codes to get better proximity gap results?
Wait, you don't need folded for this particular?
No, so here it's the important thing is the evaluation points are random. Good. So what do we show? That we show that almost all codes that were previously known to be list decodable up to capacity have firstly 1 minus r minus epsilon distance and just 2n over epsilon. So like we don't even have a poly epsilon dependence, just a strict epsilon dependence and some additive factor. Proximity gaps, correlated agreement, and like a slightly stronger notion of mutual correlated agreement as well. So these are codes like the folded Solomon codes in a similar regime as the list decoding bounds, univariate multiplicity codes in a similar regime, which I have not told you about, but similar codes. Random linear codes, AL-based codes, like these are expander-based codes, and random read Solomon. All of these codes, or almost all of the codes for which we knew optimal list decoding bounds, we now have proximity gap correlated agreement unusual. Good. So yeah, let me maybe tell you a bit about techniques. But before that, any questions? Like, is a statement somewhat clear?
Yeah, so I guess I was slightly related question. So in the very first slide, you mentioned quite correctly that indeed this property of proximity is important for proof systems.
Yeah.
So in particular, I think the proof systems I'm aware of are the ones that arise in PCB constructions.
Yes.
And all the work of code and stuff like that.
Sure.
So does any of this have any connection with those things? Maybe even vaguely. Does this result have?
Good. So maybe I won't say exactly this result, but even if you think about just as some check protocol, for example, you can think of the summation as or like some sort of commitment to like what the total sum across the Boolean cube looks like, and that some sort of code is involved on the Boolean give that code. And you can think of the multilinear extension of that also as like some code, which comes from the low degree constraints and the summation constraint. And then you can break it down into by setting it the first code word, like if x1 was 0 and x1 was 1, you break it down into two different codes now. And then you're kind of taking a random linear combination and checking if the resulting, since if either of these was not in the code, is a random linear combination not in the code. So there you're not really caring about distance, that you're just saying outside the code or inside the code. But you can imagine that there are applications where you actually care about the distance.
Okay.
So in particular, if you want to look up things like the FRI protocol is the most famous example. FRI.
FRI.
Yeah.
Sorry, that's an acronym or?
Yeah, like
Wait,
I don't remember the full form. No, it's an acronym.
Oh, okay.
There's something called deep fry also.
There's a deep fry,
I'm not
there's
kidding.
a stir, there's a word.
Yeah.
Yeah.
Sorry, I asked.
Good. So techniques. So one of the things that we do, I think, which is kind of nice, is that we come up with nice definitions, I think. And once you have these definitions, the proofs are very short. Like all the proofs are like very modular. So that is something I really like. But okay. So what are the techniques? One definition that we came up with is this definition of line decoding. So it's a clean abstraction which like kind of looks like correlated element once you see it. So informally, a code is delta comma a comma b line decodable if amongst any a code words that are close to a line, b of those are collinear. So if you remember how I viewed list decoding, amongst any L plus 1, two are equal. So I want to say collinearity is a natural notion if you go from 0 degree, which is a point, to a line. Instead of equality. So list decoding says there are not too many close by code words to an element, which is some sort of degree 0 constraint. Line decoding says there are not too many close by non-linear code words to a line, some sort of degree. So our results also actually work for higher degree constraints, like curves as well. If your linear combination was not u0 plus alpha u1, it was u0 plus alpha u1 plus alpha square u2. That is also okay. Good. So code more formally, a code is delta comma a comma b line decodable if amongst any a pairs alpha 1 c1, alpha 2 c2, alpha a ca, such that all of these are close to their respective elements. There are c comma c prime, such that this forms a line. C plus alpha I c prime is equal to ci for at least b different lines. So this is exactly the informal definition.
So the quantification on u0 u1 is that this is true for every choice of u0 u1.
Exactly.
Okay.
For every choice of u1 u1, which has this property that there are 8 pairs which are delta close, there will be c comma c prime, which has this property. So this is line decoding, and you can similarly define curve decoding. Actually close. So why do we care? There's some nice consequences. If you get 3 line decodability, which is the first non-trivial thing, like any 2 points are on a line, and just applying 3 points on a line, you can already get, you can boost it up to whatever line decodability you want, which is nice. If you have delta comma a comma n line decodability, that implies correlated linear.
No, I was thinking, like, why would you write A and B and not A and a certain fraction?
Good, because it's much easier to work for me with, like, for example, this conclusion, writing it in terms of fractions is, it's much easier to see how points work here, I think. Good, and the next thing we say is if you have some line decodability and some list decodability, like list decodability you might have because you have some great way of proving list decoding bounds, you can combine these into great correlated agreement or line decodability, whatever you want to say. So this is nice because now the dependence on n is just based on the list size, and it is not dependent on a at all. So if you earlier started with, you'll have a square n, which might be much worse than what your list size wants. So these are the things. So the lesson here is just prove line decoding. Forget about correlated agreement, all that. The thing to focus on is line decoding.
And maybe I don't immediately see why the first one is
Good.
that immediate or
Good. So amongst any a minus, like the maximum set of points amongst which any 3 are non-collinear is of size a minus 1.
yes.
The number of lines in this set is at most a square.
Okay.
Every point outside from this a square b must be on one of these lines.
Oh. Oh, I see.
So you have b on some. That is the entire argument.
Okay.
And imagine that there are much better combinatorial bounds,
Mhm.
but I don't immediately see anything, and this is enough for us at least. because of this nice property that I don't care if there is a loss here. It will all get thrown into this additive polyton. Good. So let me actually show you a proof of this, and just so that you get some idea what the proof looks like. So I want to say if a code is delta comma a comma n line decodable, then it has delta comma a over a correlated agreement. How does the proof go? We know my assumption. There are, like, if there are a points which are close, there are c comma c prime comma c1 such that distance of u0 plus alpha u1 from c prime plus alpha c1 is less than equal to delta for at least n many alphas. This is just from the line decoding. Okay. So I just rearrange this because it is having distance. I can rearrange this. The alpha is common here, u0 minus c prime. So now consider the set of coordinates in which neither of these things are equal. u0 I is not c prime I, or u1 I is not c prime. Wait, c1. This is c1. Okay, this is c1. Sorry. And T alpha is for any specific alpha. What are the subset of these points for which equality? So in particular, note that if u0 I is equal to c prime I and c1 I is equal to u1 I, then this is just not contributing to the distance ever for any alpha because both sides are 0. So I'm now asking, this T is just saying when are both sides not identically 0? Then I'm just defining T alpha for each alpha. What are the subset of these which end up being 0? Why am I doing this? The distance I can, by just this, is T minus T alpha over n. Just rewriting. The thing to note is T alpha disjoint. If either of these things is non-zero, then this equality happens for at most one alpha. So these T alphas are disjoint, in particular some T alpha must be empty. So T is less than or equal to delta n, and that is exactly what we wanted. All the proofs previously also go beyond via this logic, but it's nice to have it now abstracted. Here, in your previous question, if we only wanted, we were allowing for some slack, then only 1 over epsilon, like if I was going for delta plus epsilon slack, then just 1 over epsilon T alphas would suffice, because something would be of size delta epsilon. So you don't need n, whatever parameter you get, you'll get some result. So I also said line plus list decoding implies even better line. This I will not go into details such as the previous one, but the argument is roughly as follows. If line passes through a few points, then you know that by what we discussed is at most delta plus epsilon n, because some T alpha is at most epsilon n. So the entire line is closed. It's not maybe delta close, but it is delta plus epsilon close. I know list decoding bounds, so there are not too many closed lines.
So if you're doing list decoding on what? I mean, like on for the same code, or we have to
For the same code. I'm not going to any other code. I'm saying there were many things which are close to this line of line in my ambient space. Then there are close by lines in the code space, right?
So
Okay, good. So maybe even
the chalks will be on the.
Don't take them out of the packs, don't take this one.
Good. So what is my assumption? My code is delta comma a comma, let's say 1 over epsilon line decodable. Is it visible?
Yeah.
And I am taking now A times list size plus, let's say A times list size plus, no, list size times n plus 8 points close by. So since there are A points close by, there must be a line which has at least 1 over epsilon points. If there is a line which has 1 over epsilon points, that entire length is delta plus epsilon close.
Yeah. Okay.
So this entire line is now delta plus epsilon close. If this line had, let's say, n points, then I would anyway be done. So let me just throw out these points from my argument. They are less than n. Let me just forget about everything on this line.
Okay.
Now I'll find another line. So if I'm able to find L lines which are close by, that contributes list decodability. So this is crucial for a term to not have this poly epsilon characters. This is why we only have an n over epsilon term, because list size in these codes is going to be 1 over epsilon. Good. So I talked about these subspace-Design codes in my title, and I talked about these coded Solomon code. So why do I talk about them? The point is these additive codes have coordinates as high dimensional, and can we get more results from these instead of just single evaluation points? So I'm going to throw a definition here. Don't worry, it looks a bit stressful, but we'll get through it. An additive code C of rate R is a subspace-Design code. If are all lower dimensional spaces, in particular, I'm going to consider spaces which are even lower dimension than each coordinate. Each coordinate is like some s dimensional. I'm going to consider spaces which are less than s dimensional. So in particular, if you set any coordinate to be 0, you're putting s constraints, which is more than the dimension. So each coordinate setting to 0 is more than dimension many constraints. So here I'm saying if in expectation, when you set the ith coordinate to be 0, and you consider the subspace that is left, on average that is much lower dimension than the actual dimension, space that you started with. Why this is interesting? I'm asking this for all spaces. For some spaces, it's natural because this like entire space gets killed off for any given point. Interesting because now I'm asking this for all spaces. And that's why you need an R plus epsilon term here. Just because you can consider there would be some space which is just a linear, like one-dimensional space, which completely agrees with your, which is 0 on the first Rn fraction and nonsense everywhere else. When you set that to be 0, it does not change the dimension at all. So you can't expect anything better than R here for all spaces. I'm saying, okay, give me something close to R. This seems slightly arbitrary. How do you construct such a thing? Guruswami showed that folded Solomon codes are subspace designs. They do have this property. That is why we care about them. And recently, Venkatesan and Guruswami showed that folded random linear codes also have this property. So instead of like take a random linear code which has like many random linear codes inside, they also have this property. And now there is an understanding that all the list size bounds that we have only really rely on this property. So folded Solomon codes, whatever list size bounds are known, everything just follows from this property. You don't really need functions. So how do these proofs go on a high level? So how do we use Subspace-Designs? In the list decoding setting, Guruswami and Wang showed that all code words close to a given received word lie in a low dimensional space. But this is, they showed for folded Solomon codes only. And then their proof was very algorithmic. but you can show that this is actually true for any subspace design code. So in particular, this is not that surprising if you know the list size bounds already. Because if the list size is just 1 over epsilon, well, all close by things lie in a 1 over epsilon dimensional space. So it's not that surprising. Just take the whole span of the list. And recent works, a huge line of works, like starting from Kopati, Ramsey, Saraf, and Wouters, then Tao, Srivastav, Chen and Chang, Ashwin Kumar, Habib Srivastav, all of these works combined kind of show that very few close by codewords lie in any low dimensional space. So if all close by codewords are in a low dimensional space, and in any low dimensional space there are few codewords, well, there must be few close by codewords. So it's a very weird argument in which you're going 2 steps, but kind of works. And in Chen and Chang's argument, you can actually remove starting from here and just directly conclude this. But it's still nice to have these 2 parts, because if you are asking an algorithmic question, you can divide your question into 2 parts. So this second result kind of says list decoding bounds hold for low dimensional spaces. And in fact, the second step can be completely algorithmized for any subspace design code. The first step we only know how to do for some families, like the 48,000 code. The second we now know how to do. So how do we do line decoding? We do the exact same thing. We say all close by codewords to a given line now lie in a low dimensional space. This is slightly more surprising because now you don't have 1 over epsilon list size or anything. Because now the set of things close to everything along the line all together. So these are q over epsilon things all together lie in a low dimensional space. So I'm kind of saying that these 1 over epsilon dimensional spaces that you have along each point, they all combine into a very low dimensional space. And then we show that line decodability bounds hold for low dimensional spaces. So we can just mirror this sorts of arguments. Again, this is very clean, but I think one thing that makes this all clean is like just having the right definition of like this. The way we define subspace design codes, even though subspace designs have been around for a while, I think this maybe this precise definition was not written, like it wasn't written this. And with these, it's much easier to see why things work. Good. So step 1 is kind of an immediate-ish consequence of the definition once you stare at it long enough. The second step is slightly more interesting, so I'll talk about that. Think at the time. So we need to find all close by codewords in a low dimensional space. Let's say we are thinking of 1 minus r minus epsilon from some element. So I'm just thinking of list decoding right now. I'm not going to line decoding. So you have some element y, you have some low dimensional space, find everything close by in this low dimensional space. So KRSW, Kopati, Ronzevi, Saraf, and Wouters had this very clean idea that don't try to be too clever, just pick a random coordinate and reduce this space which is correct on this coordinates. Since you agreed on 1 minus r, since the distance was 1 minus r minus epsilon, that means you agreed on r plus epsilon fraction. So the probability that a random coordinate has the property that you agreed on it is at least r plus epsilon. But dimension also reduces with probability at most 1 minus r. At least 1 minus r. So with epsilon probability, you are in the reduced space and you agree on it. You repeat r times, you find the codeword. So this means that there are at most 1 over epsilon to the r close by codewords. One thing to note is starting from this assumption, here we use nothing about subspace designs. This is just anything for any linear code, any additive code. Question is, can you use subspace designs for the second part? We're using it for the first part to get this low dimensional space. You should be using it in the second part as well. Because, for example, one thing that subspace designs say that it does not reduce, dimension does not reduce by 1. Dimension on average reduces much faster. So you should really be using that. So recently, Ashwin Kumar, Habib, and Srivastava showed that there is a better way to sample from these coordinates. If you do uniform, maybe you're just bad, I don't know. But there is a good way to sample such that there is a good success probability. Just epsilon over r. So this also gives you a list size bound of just r over epsilon. And that is very good bound logic. This is not the optimal bound, you wanted only a 1 over epsilon. Size bound is an r over epsilon size bound. But okay, we'll live with it. So why is this interesting for us? In our work, we show that there is a way to implement this algorithm to only depend on the subspace, forgetting about the received word. It's very clear to see in KSW that what you're doing is picking a random coordinate at each step. One way you could be doing is saying, I will agree on this coordinate, so I'll just restrict to this space which agrees with my received code word on this coordinate. But the problem is in line decoding, you have many different code words. You have many different code words, so you don't know which to agree with. If you try to restrict it the same. Easy fix, just set it to be 0 and say I will agree with the thing later. I will figure out what I was agreeing with later. But just set this coordinate to be 0. Since all these things are just shifts of this space, I will figure out the shift later, just set it to be 0. We show that there is a way of doing this kind of thing even for AHS. Even though they have slightly more involved distribution, you can modify the distribution very slightly and it kind of just works. So we can run AHS on the entire line with shared randomness. So even if there were many close by things, we will find a lot of them simultaneously. So let me lay this out in a little bit more detail. So we need to prove line decoding. We have a given points which are close to the line, and there is a low dimensional space which contains all of them. Because there was a success probability of this AHS algorithm, there is some set. This P is just the success probability of your algorithm of picking these points, such that on these points, Ci of S will agree with the line with decent probability, in particular this P probability. And projecting onto these is a bilectron. In a sense, like once you fix all these coordinates, there is only a unique element. Since I'm going all the way until I reach the 0 space. I'm setting the random coordinates to 0 till I reach the 0. So you can then show that these PA code words that you receive will lie on the line. If they agreed on this set, then they must lie on the line. And I'm not writing this out, but it's easy to see that again, you can take whatever agreed on one element, you can take whatever agreed on the second element, find an element third thing that will have to agree, and by uniqueness you'll be done. So this shows that if you had a P success probability way of recovering code words, you'll get PA on time. This is exactly what. So this is line decodability. And this is enough to get line decodability for Subspace-Design codes. And if you have it for if you have line decodability, you also get correlated agreement and proximity gaps immediately. So just because we have these nice definitions and everything just fits very easily together. Like the proofs are extremely short. So I also mentioned these random read Solomon codes and random linear codes and all of these things. So I'll say a bit about them. I'm not going to too much detail about them.
Can you go back to so the the fact that you can run AHS with just the subspace.
Yes.
Something's bothering. So in the sense that if we are in the list recovery setting and not the list decodability setting,
Yes.
Guruswami Wang will still tell you that everything in your list is in a subspace.
Yes. You can run AHS. The thing is, what AHS gives you is a set of coordinates on which you're going to agree. So now on this set of coordinates, now you have like many options. L to the size of S options. If each coordinate has L options, And then outputting is at S, then it will have L to the S code words.
Oh, it'll have L to the S. Okay.
So this does give you list size bounds, and this does give you algorithms.
Okay.
And that is the other paper that we have,
Okay. Okay.
which just says that this idea is also interesting for list recovery.
Okay.
Shared randomness pruning. And actually, we started from trying to do list recovery. We weren't even thinking about this problem. And then we realized the techniques are much more interesting for this setting. At least for now. Good. So I want to talk about a bit about random read-solving codes and random linear codes. So there has been these recent lines of work which talk about these LCL properties, which somehow model list decoding, list recovery, and all these sorts of things. And they kind of recently showed that all LCL properties of random linear codes also hold for random read-solving codes. In the sense, if you have some great list size bounds for random linear codes, they will translate to great list size bounds for random read-solving codes. And similarly, vice versa. So the local properties of these codes are essentially the same, such as list coding and list recovery. Then in another work, Breckensick, Chandler, and Chan showed that all local properties of folded random linear codes also hold for random linear codes. So if you have a local property which holds for folded random linear code, doesn't matter. It will also hold for random linear codes. So if you have list decoding bounds for folded random linear codes, they will also work for random linear codes and hence random read-solving codes. Why is this nice? As I mentioned before, folded random linear codes are subspace designs, even though random linear codes aren't. So if you have some proof of some property for all subspace design codes, it will translate directly to random linear and random read-solving. If your property is all this local LCL business. Another work Geronimo showed that all LCL properties of random linear codes also hold for explicit AEL based codes, like there exist expanded based codes, which will have that. So all we now need to do is prove just whatever LCL properties we want for subspace designs, and they'll translate to everything that we want. So great, just show that line decoding is LCL. It's not exact, it's kind of LCL. Just because the framework was kind of made with these 0-degree constraints in mind, so it does not seem to capture line decoding immediately. It does not seem to be LCL immediately. So because LCL properties are built with these equality constraints in mind. So we define a related notion which we call V-decoding, which is somehow related to line decoding, which we show to be LCL, and it captures line decoding and vice versa, up to some loss and infinitors. What is this notion? I won't tell you, but I can intuitively say that it takes line decoding into lots of 0-degree constraints. Instead of one 1-degree constraint, it will break it into lots of 0-degree constraints. So this is kind of saying that if you, instead of 3 points on a line, I'll say you have one line from 2 points, you have another line from 2 points. They will agree on their evaluation weights at the 0 point. So instead of finding 3 things which are nice, I'll find 4 things which are nice, but they agree on some evaluation. If you agree on lots of evaluations from this, they are the same line. Being very big, but that is kind of the idea. And now results for V-decoding, let us transfer proximity gaps from subspace design to these other families of codes. And this is exactly what we want to do. So this does give us our results for all these families of codes. We'll say one quick, the last thing, at the end of the initial question, that maybe what we want is not exactly delta. If I allow for some slack, if a non-negligible fraction is delta close, then the entire line is delta plus gamma close. Maybe I'm willing to take some slack. So in our work, we also show if you want constant proximity loss, this quantity is called, the gamma is called the proximity loss, and constant error, like epsilon is constant size field size. you don't need to go to n size field or q size field. Like you don't need to go to very large fields or very large alphabets. And random linear codes will work, and these explicit expanded based codes will also work. Good. So I'll just flash our results and I'll stop. Take questions about this and this those. Okay. Cool. Thank you. Yeah.
So, in the previous, we just go back to the previous slide. So, no, just so typically in these settings, I should be thinking of n and q as basically up to constants.
No, so I think q they take 2 to the 128 or something, which is much larger than n, which they take like 2 to the 20. I don't know what these numbers mean, but
Constants.
No,
No,
if you have a cryptographic application, if you have like a security parameter lambda, then this is like 2 to the lambda that you should have.
Oh,
So-
I see. Okay, so q is typically way larger than n.
Yes.
Okay. See. Okay.
I think even for standard read solving codes, there's some subtlety in this Q versus N trade-off based on whether you want, whether you're looking at, you want the statement to hold for every read solving code, meaning for every setting of evaluation points, or you want it for, or you only care about say random set of evaluation points. Remember Shubhangi mentioning this in our talk at SPTs. I think there are bad configurations. This is based on that's some property evaluation type. Okay, lifting those examples to bad configuration.
Yeah, but they're I think slightly beyond 1 minus like they're in this 1 minus r. And
They're 1 minus R mass.
kind of like they're not quite
At Johnson.
yeah. I think so.
But
Like,
I think one of the recent papers mentioned something just beyond Johnson. So there's some. If you're not, if you're happy with the
yeah.
mix of non-constant rate.
Good.
Yeah,
So they get at they'll take very low rate codewords.
Right.
And so they'll like it will be like how close you there'll be some parameter.
Right.
Like how many codewords you want, like if you want to enter the delta,
Right.
enter the lambda, enter the lambda codewords, then there is some dependence on lambda. And you can show that there is like 1 minus, like you can't get up to 1 minus epsilon. And the list decode argues
So there are-
similar to
yeah.
because it's very similar, it's not
Yeah. This is like what happens in DKR also.
exactly.
For low rate.
So it's like 1 minus epsilon versus 1 minus 4 epsilon kind of thing. I can show you the example later, it's very clear.
So the connection between subspace property, subspace design property, and list decoding, does it also go in the river? Is there an equivalence sort of,
That if you have some
if you
So I
have
mean-
list, I mean, does list decodability, the standard classical list decodability, does this imply subspace design in a black box? That we don't know.
it shouldn't in the sense of like random linear codes will not have subspace design because
They won't have, I think. Because the dimension will only fall by
One.
one.
but one thing which is nice is like I showed you this connection of like folded random linear codes, thus random linear codes. You can actually go in the other direction if there is some property of random linear codes, it will hold subspace designs.
I see. So what about if you take a folded random linear code, does list hold?
That is just a subspace design, so then you can just use.
But a folded code, if you have list decoding properties,
It will translate to the unfolded code, if it's a random thing. Kind of. Like a folded random linear code has same properties as random linear codes.
no, well, I mean, what I'm wondering is, true, if you're looking at a code over FQ, if there's no folding, then we can't expect this. But suppose you have an arbitrary code with alphabet FQ to the S, that is list decodable with whatever, good bounds.
Let's see.
Does this imply a black box subspace design property also?
About it.
Because the other direction, you Yeah.
Yeah,
that's
that's
right.
I thought so. More questions?
If not, let's thank Rohan. Maybe.